Okay, well now, these functions, a cosine of omega t plus phi, a sine of omega t plus phi, and any function in this form by trigonometric identities can be put into this form or this form. So these forms are just equivalent to these forms. But if you have a function in this form, let's just take the a cosine of omega t plus phi. Now that's the same as a sine of omega t plus phi. Your phi is going to be 90 degrees different than the phi you would have here, but you don't have to worry about that. Let's just take this so we understand this model. So we draw a circle of radius a centered at the origin. Now we know that if we have a point on the circle, then the angle theta from the positive x-axis around here, if the angle of the radial line from the origin to the point is theta, as measured counterclockwise from the positive x-axis, then the cosine of theta is just the x-coordinate of this coordinate, of this point. Now, if, and I haven't drawn it in here, and maybe I kind of should have, okay, if you have a phi, and you have some angular frequency omega, then if the angle between the radial line making angle phi with the positive x-axis and the radial line to this point at angle theta on your circle is omega t, okay, so that would be the smallest angle we have in here. It's written kind of small. But we've got phi, and then we've got omega t, and theta is made up of phi and omega t. Theta is phi plus omega t. Now, we interpret t as our parameter, or usually as time. So multiplying omega by t, omega is just angular velocity in radians per second. You multiply that by t, omega doesn't have to be in radians per second, it can be in degrees per second, revolutions per second, RPM, revolutions per minute, anything. But when you're doing the mathematics, you want to use the default units of radian for your angle. And if t is measured in seconds, you would want to measure omega in radians per second. Anyhow, if you multiply omega in units of angle per time, over time, multiplied by t in units of time, you get an angle. And if omega is positive, and t is time, and time keeps increasing, this angle keeps increasing. And it keeps increasing and increasing. It can go through any number of revolutions, still increasing. And what that does, of course, is it takes this point around the circle and around the circle and around the circle. Well, okay. X equals a cosine theta. If theta equals omega t plus phi, which I've attempted to depict here, then x equals a cosine of omega t plus phi. That makes x a function of t, and in that case, if t is interpreted as time, the motion of this point on the x-axis to which the point on the circle projects undergoes simple harmonic motion according to this equation. Okay? Now, this form is the same as this form and follows immediately from this condition. Now, there's a more general condition that makes this happen, but certainly for a pendulum of low amplitude with no extraneous forces, this gives a good model of the motion of the pendulum. Okay? Now, so the pendulum can be thought of as going back and forth according to this model. Where does it start? Well, it starts here. If it starts at t equals 0, this is where it is at t equals 0. Then the angle starts increasing from here and goes around, so it starts here, and the x-coordinate will move over to here and back to here and over to here and back to here again and again. So you have the back and forth motion of the pendulum. Okay, there's our model. Question now, how long does it take to complete a cycle? Well, assuming omega is in radians per second, it could be in other units, and you could reason it out very similarly, but whatever the units of omega, if it's in radians per second, a cycle means you go all the way around the circle. It means you go from this point, and in this case, you're going to start moving to the left, and you're going to move to the right. You're going to go past the point and come back to here. That's a complete cycle. You're ready to start exactly the same motion over again. What's the change in the angle for a cycle? Well, we go all the way around the circle. What's the change in angle as you go around the circle? Well, that's defined to be the arc distance you travel divided by the radius, isn't it? Because that's the definition of a radian. Divide the arc distance by the radius, you get the number of radians. So that the arc distance is equal to the radius times the angle in radians. Arc distance around this entire circle is 2 pi a, which means, since the radius is a, of course we understand that the circumference of a circle is equal to pi times the diameter, which of course is 2 pi times the radius. Radius is a. So all the way around, circumference is 2 pi a. You divide that by the radius, which is a, you end up with 2 pi radians. So to complete a cycle, theta has to change by 2 pi radians. Well, at what rate is it changing? Well, that's omega. And if omega is measured in radians per second, then you would have 2 pi radians divided by omega radians per second. It would give you the number of seconds that it takes to go around. And that's how long it takes to complete a cycle, and that's how long it takes your pendulum to complete a cycle. Now, for the pendulum, remember omega is the square root of g over L. We made that assumption right here. So, if we know the acceleration of gravity, which is pretty much constant anywhere we go, and divide that by the length of the pendulum and take the square root, you get omega, and then you can use it to determine the time it takes the pendulum to complete a cycle.